Equations of motion by graphical method. Motion of an object was studied by Newton and then it was summarized in a set of equations of motion. The equations analyze rectilinear motion of uniformly accelerated body. The motion of such a body can be well predicted with the help of a set of three equations called kinematical equations. A body is moving along a straight line with initial velocity u. After time interval t, it attains final velocity v due to an acceleration a. Then the set of three equations is given as v is equal to u plus a multiplied by t. This is the first equation and it represents velocity-time relation. S is equal to u multiplied by t plus half multiplied by a multiplied by t squared. This is the second equation and it describes position-time relation. V squared is equal to u squared plus 2 multiplied by a multiplied by s. This is the third equation and it represents relation between position and velocity. These equations can be derived by graphical method. Let us see them one by one. 1. Equation for velocity-time relation. An object having non-zero initial velocity u starts from point P. Its velocity goes on increasing with respect to time and becomes v when it reaches point Q. The change in velocity is at uniform rate. A is equal to change in velocity divided by time. A is equal to Q multiplied by P divided by T. Therefore, Q multiplied by P is equal to A multiplied by T. To find change in velocity, draw line PR parallel to OS. Distance QS is equal to distance QR plus RS. Therefore, distance QS is equal to distance QR plus PT since RS is equal to PT. Substitute the values of QS with V, PT with U and QR with A multiplied by T. We get V is equal to A multiplied by T plus U, or V is equal to U plus A multiplied by T. The velocity-time relation is obtained here. This is the first kinematical equation. 2. Equation for position-time relation. Let distance travelled by the object be s in the time interval t under uniform acceleration a. In the figure, the distance travelled is given by area enclosed within TPQS. S is equal to the area of quadrilateral TPQS. S is equal to the area of rectangle PRST plus area of triangle PRQ. We know that the area of any rectangle is length multiplied by breadth and the area of a triangle is half multiplied by the base into height. Therefore, we have S is equal to TS multiplied by TP plus half PR multiplied by QR. But TP is equal to U and TS is equal to PR is equal to T and QR is equal to A multiplied by T. Therefore, on substituting the values, we have S is equal to U multiplied by T plus half multiplied by A multiplied by T square. This is the second kinematical equation. 3. Equation for position-velocity relation. The distance s travelled by object in time t under uniform acceleration A is given by area enclosed within quadrilateral TPQS. S is equal to the area of trapezium TPQS. S is equal to half multiplied by the sum of QS and TP multiplied by TS. Substituting the values of TP as U, QS as V, and OS as T, we have, therefore, S is equal to half multiplied by the sum of V and U multiplied by T. From velocity-time relation, we have A is equal to V minus U divided by T. On multiplying both the sides by T, we have T is equal to V minus U divided by A. Therefore, we have S is equal to half multiplied by the sum of V and U multiplied by V minus U divided by A. Therefore, we have 2 multiplied by A multiplied by S is equal to V square minus U square. On adding U squared on both the sides, we have V square is equal to U square plus 2 multiplied by A multiplied by S. This is the third kinematical equation.